vessel. That's another extracellular compartment that has plasma in it, which is the liquid part of your blood. And then we have another tube here. That would be your lymph vessel. And within it is lymph. So all of these fluids, lymph, plasma, interstitial fluid, it's all outside of the cells. It's all extracellular. Again, that's the other third. And actually, one of the main reasons that I present this is not that I'm too terribly concerned about that you know where water is. I want you to know what these terms mean. All right? So when I say compartment, immediately you know I'm talking about something here. If I say intracellular compartment, you know it's inside the cell. All right? If I say the interstitial fluid, you know that it is a compartment, the fluid that bathes our cells. And so again, from now on, I will use these terms freely. Okay? And for the next 2 semesters. All right? Transcellular, where is that? Where would that be in this picture? Well, it really wouldn't be in that picture, at least drawn well. Transcellular would be things like fluid in your joints. Synovial fluid, for example. You guys are going to learn about articulations in a few weeks. Your joints need this fluid so that they work properly, so that the cartilage doesn't grind against each other. Fluid of the eye. Your eye, believe it or not, is made up of 80% fluid. That would be a transcellular fluid. Urine would be a transcellular fluid. Okay? Are we good with these terms? All right? And where water is, how much water is here, how much water is there. All right? And that's all I need to know, or that's all we need to talk about right now. Now, let's talk about the physics of water. What does water do? Water mixes stuff. It mixes really little things, medium-sized things, and it also mixes big things. All of these compartments that we just discussed, whether it be the interstitial fluid, whether it be plasma, whether it be lymph, doesn't matter. Any of them are all 3. All of those compartments and the fluids that reside within them, and so we can go back to the picture really quick. These compartments that we just drew, let's take the interstitial fluid for example. Here in this compartment, there's fluid. In that fluid, it's mostly water. And in that water, we have little teeny things in that water like sodium and potassium and chloride and hydrogen. So that's a solution. So we can call it a solution because it's water with little teeny things in it like those. We can also call the interstitial compartment a colloid. Why? Because it also has bigger things in it, like what? Protein. And as soon as you hear the word colloid for the next 2 semesters and beyond, you should think protein, because most often that's what it's referring to. So when you hear colloid, you know that protein is involved. All right? And proteins are much bigger molecules than sodium or potassium or chloride or hydrogen ions. And that's why it's called a colloid, because the molecules are simply bigger. We can also call this interstitial compartment a suspension. A suspension is water with bigger stuff in it, pieces of cells or cells themselves. Does the interstitial compartment have a cell in it right now? Yeah, it's right there. The interstitial fluid is bathing the cell. Take a grape, it's a cell, throw it in a glass of water. The water is the interstitial fluid. Your cells are bathed in fluid. That fluid is an interstitial fluid. So your interstitial compartment contains interstitial fluid that is a solution because it has little things like sodium in it, have medium-sized things like protein in it, and have big things in it like cells, for example. Your plasma, your blood, has cells in it, right? You guys have heard of red blood cells, have you not? White blood cells, those are cells. Platelets are pieces of cells. So your blood, your plasma is a suspension. That's the example I gave in your notes if you look at your notes. Your plasma has protein in it. Plasma proteins, as you'll learn next semester in a ton of detail. Your blood has sodium in it, potassium, and chloride, and hydrogen, and bicarbonate, carbonate, and calcium, and magnesium, blah, 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 blah. So, again, regardless of which of these fluids we're talking about that are contained in all these compartments, they're all 3. Okay? Are we good? So now I can use those words freely. I can say solution, I know you know what I mean. And colloid, and suspension, you know what I mean. All right? Very straightforward stuff. Now, What else does water do? Transport stuff. Okay, you guys have learned about the major systems of the body, right? You guys talked a little bit about the circulatory system. Circulatory system circulates stuff. How does it get circulated? Your blood. Your blood is a lot of water. About half of your blood is water, roughly. And it's taking stuff from point A to point B. That's how your cells live. Fluid electrolyte balance, something we'll talk about next semester. This all has to do with a molecule of water helping balance other things in the body, like electrolytes, for example. It'll help balance pH, it'll help balance a whole bunch of stuff. We already talked about what water does when it comes to cooling your body and sweat. Helps maintain homeostasis in general. Again, that's a common theme here. Regardless of what molecule we talk about, it's all about homeostasis when we talk about phys, because that's what physiology is. If somebody asks you, give me one word for physiology, immediately what should come to your mind is homeostasis, or vice versa. If somebody said homeostasis and you're supposed to spit back a word at them, phys, because that's just what it is. Okay? Good? This we're not going to spend a whole lot of time on, the second inorganic, and that's electrolytes. Well, that's spelled incorrectly there. I'll assume it's spelled correctly in your notes. Ions, it's the same thing. Okay, we have these small charged particles here that when they're in water make up a solution, by the way. Now, I have a number of abbreviations here. These are some of the basics: sodium, potassium, calcium, chloride, bicarb, carbonate, phosphate. I assume that you know what those are. So on the exam, I will have every once in a while abbreviations of molecules. It'll be nothing foreign to you. It'll be something that we specifically talked about in class, but you need to know what they are. Again, I'm just going to assume that you do it. If you don't, certainly I would learn it. Okay? When it comes to these ions, these charged molecules, these small charged molecules, they're in equilibrium. They make salts. So these charged ions come together to make salts. When we hear salt, we always think of sodium chloride, right? But this is a salt. Potassium chloride is a salt. Calcium phosphate is a salt. Calcium carbonate is a salt. It's just not table salt. We don't sprinkle those on our French fries, right? These are other types of salts, but they exist within our body because we have these other molecules that exist, and we have this equilibrium, this chemical reaction that's occurring. That I'm going to assume, once again, you guys understand. All right? And we have to have normal values for these. There has to be a normal sodium level in your body, or things are going to go wrong. And when I say go wrong, what kind of things? Well, I'll tell you later. But worst case scenario is death. All right? Or at a minimum, you're having a crappy day. Yes, sir?
The positive charge are molecules are. Oh, wait a minute.
You good?
Yeah, it's already said.
Okay. All right. So these things do a number of things. They help us with communication. Action potentials, we're going to talk about that in a lot of detail in some weeks to come. All right. They're going to help us transport stuff across membranes. We're going to talk about that actually next week. And again, it's all about homeostasis. So I'm not spending a whole lot of time on this right now because we don't need to. Okay? And then the last thing here that we'll talk about, and maybe I'll give you a teeny bit of a break, although we're already a little bit behind. What time we get out of here?
6.
6? We got here at 6? Oh, you're not getting a break today. I'm sorry. I always give you a break in between lectures. I started a little bit late, plus we had some computer glitches, but I'll always give you a break sometime in between the class. I get about 35 or 40 minutes, I promise. Okay, today was an exception. All right, acids and bases. If we talk about acids and bases, we have to talk about pH. And a lot of times pH intimidates people. pH is very straightforward and easy. So just a really quick pH lesson here. So when it comes to pH, what is pH? It's the power of H. H is an ion, an H ion, charged positively. It's also called a proton. So those of you that have taken chemistry classes, and everybody here has, okay, you'll hear the word proton, proton, proton. It's an H ion. It's the same exact thing. And so when it comes to pH, what is pH? Well, we're going to draw two separate containers. I'm going to call it A and B. And in each of these is water. We're going to assume that it's the same volume of water. Those are all protons. Those are all H ions. Now, obviously, I drew more H ions in B than I did in A. So obviously, the concentration of H ions is higher in A or B. obviously it's B, right? So we have a higher H plus concentration in in B as compared to A. Okay? Now that's going to dictate what pH is, because that's what pH is. pH is a measured value. Okay, and there are numbers that are associated with pH. It's a unitless number, but it tells us what the concentration of pH is. And so when your H concentration is higher, your pH is lower or higher. We have to compare A and B. Which one has a higher pH, which one has a lower pH? We'll start with lower. The lower pH is in B, right? So this is going to have a lower pH. There's an inverse relationship between H plus concentration and pH. So this is obviously going to have a higher pH. So of these two, which one's more acidic? B's more acidic. The lower your pH, the more acid we have. And that's what H plus is in essence. That's what the acid is. So this one is more acidic. This one's less acidic, or more basic, if that's what you want to call it. That's all pH is. So we have pH values of what? 5, 6, 7, 8, 7.3, 7.4, 7.5. And by the way, I want you to know what the normal value is in your blood, your arterial blood. It's in your nose. So if we were to draw our homeostatic level for pH in our arterial blood, there's our set point. Arterial, that's the blood in your arteries. Arteries are a specific type of blood vessel that take blood to your cells. We'll talk about it in a lot of detail next semester. So your arterial blood pH, a very important value that is measured routinely clinically. The set point is 7.40. Obviously, we have a normal range. And our normal range is anywhere from 7.45 to 7.35. A very, very narrow range, but very important that it be maintained. Okay? To a chemist, that's peanuts. In the body, that's huge. You have a patient, and they have a pH value that's even, is 7, that's neutral, right? 7 is a neutral pH. 7, if your patient has a pH of 7, you're panicking. Your patient might very well die because their pH is 7 or 8. That's bad. Okay? So it has to be maintained within a very narrow range. And I'll tell you why later. Probably on Monday, I'll tell you why. Okay, tonight I'm not going to have time. But I do want you to know the normal range for pH in the arterial blood. All right? And we're going to talk a ton about pH next semester when we go into acid-base balance. We'll visit it a little bit this semester. Now, when it comes to the actual numbers, so I just said 7.35 to 7.45. Well, what on earth does that tell us about H plus concentration? How do we translate that? We do it simply with scientific notation here. So a pH of 7.4, for example, that's our set point value. How do we know what the H plus concentration is? Because that's what pH is measuring, right? pH is measuring the concentration of H plus. 10 to the negative 7.4. That's your concentration of H plus right there. If you have a pH of 7.4, I don't care. I don't care. That's what the value is. Do you have to know these specific numbers? Absolutely not. I'm not going to memorize this stuff. All right? But I'm going to assume that we know scientific notation. And I'm going to assume that we know how to read little teeny numbers like this. All right? And by the way, the practice exam is already on Pilot. And you'll see on that practice exam the kind of questions they'll ask that revolve around something like this, and every other thing that we're going to talk about for the first exam. Okay, so it's already on Pilot, and I encourage you to go to the exam and look at it now. I put the correct answers in a key at the end of the exam. You don't have to look at the key. Just look at the questions. All right? That'll kind of give you an idea of how to study. That'll kind of give you an idea of how to put the ideas, or how to put the material together, and how to integrate it, as I said in that email to you guys. Physiology, you need to integrate information. You need to be able to put it together. And if you can't do that, then you're going to be in trouble. All right? And if you don't know how to do that, that's when you get help from me, from the tutors, you know, the TAs, whomever. All right?